Hey guys. So, anybody in here yet? Fairly new to streaming. I don't know why I feel like I'm a little bit more anxious about this than I am with teaching. Being in front of a whole bunch of critical students seems to be less intimidating than being online in front of maybe two people who might be watching this. Anyway, So today, my plan is to just go and talk about some of the stuff that I've been doing in my book. So I'm writing a textbook on data-driven methods and dynamical systems, and a lot of it touches on very fundamental functional analysis and operator theory. So I've been talking a lot about the more Fourier transform L2 spaces on my channel. I actually have a couple of videos coming out soon that go further into all that stuff, talking about the Hermite functions as a basis, which we haven't done on the channel before, and also talking about divergent integrals and how that's connected to the Fourier transform. So that should be interesting. But for today, I was going to take a different angle. So I've been working on this chapter for operator theory for a bit, while I've also been making the content for the Fourier transform stuff, which is also going into another chapter. And I thought I'd talk about it for a bit and see if we can get into some details about operator theory, operators, linear operators, and ultimately, after doing a few of these streams, I would like to get up to the spectral theorem. We'll see how far we can get with all that. And so some of this stuff is going to come down to talking about Hilbert spaces and matrices and all that good stuff, and so I'm still trying to figure out exactly where to start with all this stuff. My chapter notes aren't exactly the most coherent, but yeah. Anyway, so while we collect people and get started, I could probably stream for about an hour or so. I can show you some neat stuff I've been showing my differential equations class, which I'm teaching right now, and that is how to use a Picard theorem to give a complete definition of the exponential function, which I thought was pretty neat. And then that'll only take a minute to go over, and maybe I'll make a video out of this, I don't know. And then after that, we can get into some more proper operator theory stuff and talk about Hilbert spaces and operators on them. Does anybody have any questions or anything you want to know before we get started? Okay, which is really handy for doing any sort of note taking and doing a lot of math. In fact, it even will transcribe some math equations into just LaTeX if you ask it to. It's not super great at that, but it'll try. So let's go ahead and start. If you remember the Picard theorem, Lindelof theorem. It basically, this is a very special case I'm going to write down. It really comes down to Lipschitz continuity and things like that. But, I'm just going to say that if, so we'll say the initial value problem and this is the initial value problem, and we'll say y prime is equal to f of ty, and with the caveat that y of t0 is equal to y0, has a unique solution if f and the partial derivative f with respect to y are both continuous in a neighborhood of T naught Y naught. Right, so that's a fairly handy theorem. this can be changed and modified in a lot of ways. We can change the continuity of this guy, exchange that for just being Lipschitz continuous, which is the more general version of this. But when you're teaching like differential equations in undergrads, you usually don't talk about that sort of thing. And then one of the things we can change, if it turns out that, say, moreover, if, say, let's lean into this Lipschitz continuity a little bit. So f of ty minus f of t tilde is less than or equal to y minus y tilde times some constant. Then, for all y in R, then the solution is unique and defined for all t. Right, and so that's the thing with the I should say, yeah. So we have modified the Picard theorem a little bit here. So what I'm saying is that this actually works out for all t, for what I'm doing. So for all y, like this, I'm saying it works all the time. It satisfies this Lipschitz continuity condition, and if you have that, then you have it. The solution is defined for all time. Now, if you only allow this to work in a sort of a local neighborhood, so you get rid of this for all y, then you can only trust that the solution is going to exist for some small delta time. But what's really nice with this is that it tells us that our solution is going to be what is called forward complete, which means it'll exist for all time, which means that we can apply our apply this existence uniqueness to things like linear equations. So the Picard theorem says that the initial value problem we'll say y prime is equal to y and y of 0 is equal to 1 has a solution for all time, and that solution is unique. Okay, so what's neat here, okay, so if you know some calculus, then you know that this differential equation, this initial value problem, is very quickly solved by just taking e to the t. So the derivative of e to the t is just e to the t, and if you set t equals 0, you get 1. So that works out really great. But let's say we don't know what the exponential function is. So let's pretend we don't know y of t is equal to e to the t. So we've never heard of the exponential function before. Now you can actually reconstruct the exponential function a lot here, and so you can get a lot of really cool stuff. So for instance, we'll just define y, the solution here, as we'll just give it a name and we'll call it the exp function. So we don't know it's an exponential function, we don't know anything about it. And what we're going to do is we're going to develop the different properties of this exponential function, and then we're going to show that we have like the splitting over the we split the exponential function splits the the addition into multiplication sort of acts as a homomorphism, if you know what that term is. And yeah, that's pretty nice. And then we can even get show that the Fourier that the Taylor series also, we can get the Taylor series representation for the exponential function here too. So let's do the Taylor series one first, because that's kind of fun to work out. So we could come up with the Taylor series in two different ways. If we're using the Picard theorem, we could just use Picard iteration, and that will slowly spit out a series, and that's fine. But we can also just try putting in a series into the differential equation and see what we end up getting out. And if we do that, then we know that once we find a series that matches that differential equation and that initial value problem, it has to agree with this guy by the existence and uniqueness theorem. So that's how we're going to get all these sort of identifications, which is really nice. So for instance, I could take y of t is equal to, we're going to assume y of t then is representable as a power series. And then we will need y prime of t, which will give me the sum n equals 0 to infinity of n times a n times tn minus 1, or we can adjust that a little bit, and that's going to give us the sum of n equals 0 to infinity of n plus 1 times a sub n plus 1 times ttn. And I can drop the 0 and shift this to 1, I think. Is that right? No, it's going to start me at 2. Sorry. 0. Yeah, okay, so I didn't have to shift that index backwards because this guy was shiftable to 1. Sorry. I have to keep track of your entities. Okay, so if that is true, then if y of 0, by the way, is equal to 1, then that tells us that a of 0 is equal to 1. So that gives us something to start with. And otherwise, y prime of t equals y of t. That's going to give me an is equal to n plus 1 times an plus 1. And so then I can get that an plus 1, if we have an, like we have a0, we can get an plus 1 by dividing by n plus 1. And so from here, what we do is we just start with a0 is equal to 1. Then we see that a1 is equal to did I get that right? Oh yeah, so a1 here is going to be 1 over 1. And then a2 becomes a1 over 2. And so that's going to be 1 over 1 times 2. a3, you can see what's happening, 1 times 2 times 3, etc. So then an becomes 1 over n factorial, and so that tells us that we get y of t then, if the power series does converge, 1 over n factorial times t to the n equals 0 to infinity. And indeed, that is a convergent power series for any t. And so we have an entire function here, and so then that must match our other function, expt, because they both satisfy the same differential equation. So by the Picard existence and uniqueness theorem, they match, and they match for all t, because this is a globally Lipschitz dynamics or differential equation. So how can I get so there's two routes then for figuring out the properties of the exponential function. So one route is, so thus far we have y prime is equal to y, and y of 0 is equal to 1, and we have defined it to be y of t is equal to the exponential of t. We don't know any properties about it yet, but what we did just demonstrate is that it does have this Taylor series expansion, right, which is kind of cool. Okay, so what we can do next, if we want to get the product definition here, yeah, okay, yeah, sure, I'll fix the, I'll make myself smaller. There we go. Is that better? Sorry, I missed that, chat. All right. Let's see. Then, yeah. So now our objective is to take this, and we can try to find the multiplicative property. And so our claim here is that exponential of t plus, I don't know, tau, that might be an unfortunate choice, is equal to the exponential of t times the exponential of tau. And we would like to prove that. One way to prove that is you can go and the power series, and you can expand that out, and that would be a real pain in the butt. But you can use you can exploit the properties of the Picard theorem again to get this, which is pretty handy. So, so our proof of the claim. Let's see. So what we'll do is we'll make a new initial value problem that we would like to solve. So I'd say take a look at, say, y prime. So I'll say y tilde prime is equal to y tilde. We're still looking at that same differential equation, but I'm just going to change y of 0. And I want this to just be e to the a for some a in R. Or I shouldn't say e to the a, I should say exponential of a. So we have this function exponential of a, and that is well defined because of the Picard theorem. And yeah, so this is exponential of a is some real number. I don't know what it is. We haven't figured that out yet, but we can work with that. Yeah, cool. Yeah, and let me know if there's anything wrong with the audio or anything like that. If the music's too loud, if you can even hear the music, I have no idea. Just let me know. Yell at me. I'm new at this. I'm used to doing recordings that I have scripted out and worked out for 2 weeks to a month or so. And so doing this all live off the cuff, it's not entirely foreign to me because I am a professor and I do teach this stuff, but there's a new kind of anxiety that comes with this stuff and all this technology. Okay, so here we have this initial value problem, and what we can get then is this. So we have, so we're essentially going to show that these two things are more or less the same. So let's see, how would I do that? So on one hand, I have that, let's see, so if I take, that should be y tilde. So this does have a solution of some kind, and so this is going to be, so y tilde of t is going to be equal to, let's see, best way to do this. I did this in class the other day. It's driving me crazy. I should be able to do this off the top of my head. All right, anyway. So one thing we can note is this. So consider h of t plus a. H of t defined to be the exponential function of t plus a. Okay. And if I have that, then I have that h prime of t is equal to h of t, and I have that h of 0 is equal to the exponential function at 0 plus a, or just the exponential function at a. So in this case, so I see that h of t should be equal to whatever this y tilde of t is. So we have that it is equal to, cool, thanks guys, is equal to this. So then, so I have h of t is equal to y tilde of t. So now we need to find another way to represent this. And so what we can do is we can try try the other one. And so let's say g of t is now equal to the exponential function at a, and we're going to throw in the exponential at t. Now in this case, we see that g prime of t is equal to the exponential of a times exponential of t again, just because the derivative of the exponential function is itself. That is by its definition according to our Picard iteration. And so then we see then that g prime of t is indeed equal to g of t, and since we defined the exponential function as 0 to be equal to 1, and that's because it satisfies the initial value problem up here, then that means that g of 0 is equal to the exponential at a times exponential at 0, or exponential of a times 1. And hence, g of t is also equal to y tilde of t, but we already said that was equal to h of t, and that tells us then that the exponential function of t plus a is equal to the exponential function of a times exponential function of t. And so we have now actually satisfied, we have demonstrated this property of the exponential function, right? So that's pretty nice. Okay, so using this, Picard iteration and the existence, and in particular the uniqueness that we get out of that theorem, we can establish all of these identities for the exponential function. All right, let's see. Yeah. Okay. Yeah, that's probably right. Yeah, I know. I'm just doing this all off the cuff. Your method is probably more efficient. But yeah, absolutely, that would work. All right. So one last thing I would like to do on this, and remember we're going here assuming that we don't know what the anything about the exponential function is, and so in particular we don't know what the e is, right? The 2.72 or whatever, or 2.71. Oh, well, anyway. So the question is, what is exponential of 1? In other words, e. And you can get it this way too, and using differential equations. And so what we can do is we can actually turn to Euler's method. Which is pretty cool. And so if you don't know Euler's method off the top of your head, it's basically this. We're going to say y of 0 is equal to y, the initial value. And we're going to say that yn plus 1 is equal to y of n plus h times f at, say, tn yn. So this is really basic Euler's method. And so what we would like to do, and basically what happens is as h goes to 0, that you have that, yn, it becomes approximately, or say, let's see. So basically what we're going to have is we have y of n times h minus y of n, and this difference should go to 0. And so what's really cool is we can actually set, as approximate. So we want to. So our goal here is to approximate y of 1, or in our case, exponential of 1, using this method. And so what we're going to do is we're going to set h is equal to 1 over n, and for some n that we might specify, and then we're going to do n steps to get to 1. So then n steps to 1. Okay, so then what we see then, all right, so we start with y of 0 is equal to 1. That's just our initial value problem, and that's what we have. Then you can get y of 1 is equal to 1 plus h, which is 1 over n. And then this, we're going to have f of say 0, comma 1, and where f, remember, is we're assuming that we have y prime is equal to y, and that is our f of xy. And so in this case, f is equal to y, and so it's going to be times 1. Okay, that's, just first step, no big deal. Then we go in y2, and we're going to have take our y1 plus 1 over n times f of y1, which is going to end up giving us 1, well, I'll just say times y1, and so we end up getting 1 plus 1 over n plus 1 over n times 1 plus 1 over n. And so then this becomes 1 plus 1 over n times 1 plus 1 over n, or 1 plus 1 over n squared. And so, and then what you can do is you can just keep iterating this, and then you'll see that ultimately you get y sub n is equal to 1 plus 1 over n to the nth power, and you can prove this by induction. And but y of n is supposed to be approximating y of 1, and so that tells us that the limit as n goes to infinity of 1 plus 1 over n to the nth power is equal to the exponential function at 1, or if we want, we'll just define this to be e. And so I think that's pretty cool. So not knowing anything about the exponential function or any of that, we started with just, the derivative definition of the exponential function, used the Picard, existence and uniqueness theorem in order to gain all of these, properties of the exponential function, get its show that the Taylor series actually agrees with the exponential function, and then even after all of that, we have even come up with this identity for finding E, and that is by using the convergence properties of Euler's method and this just linear differential equation. So Euler's method, theoretically should work out. Of course, in practice, Euler's method might not be the best choice and for any arbitrary differential equation, but for here, it works out pretty well. Okay, so let's see. All right, so it's 12:22. So let's go ahead and start sketching out what I want to talk about. So this exponential function stuff, it's all bonus stuff for anybody who wants to just jump in early on in here. But let's talk about operator theory. So Picard's theorem, it also dips into operator theory, and there we have, with Picard's iteration, a nonlinear operator that basically spits out, that ends up being contractive, and it takes an approximation of what the initial value problem is, and then it keeps iterating it, and it gets better and better. But if we want to talk about all this stuff, we need to start introducing a lot of other things to do with operators and these spaces and stuff like that. In particular, what I'm going to talk about, I want to talk to you guys about Hilbert spaces a little bit. If you don't know anything about Hilbert spaces or vector spaces or things like that, well, if you know anything about vector spaces, this might go over your head anyway. But we want to have these operators posed over something. So we can use Hilbert spaces. In a more general functional analysis course, we would talk about Banach spaces. So this would be like the space of continuous functions and things like that. Hilbert spaces include things like L2 or the Hardy space or a bunch of these other guys. So I'll put like L2 of R, we have L2 of say 0, 1, H2 of the disk, etc. And with Hilbert spaces, there's some things we should review. So inner products are a big one. We should also talk about the Reese representation theorem. And and maybe projections. We'll see if we get to that or not. We can talk to that another one. So projections. And the general goal for operator theory the things I want to talk to you about, maybe not all today, but basically what operators are. We'll talk about linear operators in particular. I want to talk to you about, let's see, inversion, because that's going to be really important when we want to talk about spectrum. And the various kinds of spectrum. So, we have our point spectrum. We have our continuous spectrum. Etc. And give you examples of each of these guys, probably revolving around what we would call the shift operator over the Hardy space. It's probably the easiest place to talk about a lot of that stuff. Let's see. So, and what else do I want to talk about? And so our ultimate build-up, what I would like to get to through like a series of these videos. Probably not today, but I want to talk to you about compact operators, and then the spectral theorem. I don't know how far I want to go with spectral theorem. So the sort of minimum thing you should probably know from the spectral theorem would correspond to self-adjoint compact operators, which comes up quite a lot. Which basically says that every self-adjoint compact operator is diagonalizable. And then we can expand that to normal operators and other cases, and then maybe a little bit outside of the compact operators, but that requires a little bit more of a framework that I'm not sure we'll be able to get to, maybe even this semester if I aim at that. I don't know. But that's more or less the stuff I would like to talk to you guys about. And so probably today, starting at least laying out our basic Hilbert spaces and talking about maybe some basic operators over them. Do you guys have any questions before we start? Okay. All right. Well, if no questions, I guess we can get started. So, all right. So, what is a Hilbert space? And by the way, later today, I'll try to export these notes and upload them to my Discord server, which you can find in probably the About page on my YouTube channel if I forget to put it in the description here. And so then if you guys want to review that stuff, you'll have that available to you. So Hilbert space, or Hilbert spaces. If you say Hilbert space, usually people are talking about L2. But Hilbert spaces, it includes the whole variety. For a long time, basically in the early 19... Hilbert spaces came about first with Hilbert working on spectral problems, and in like Sturm-Liouville problems, I think, if I remember right. Anyway, but he was working with a sequence space, so he was working with little L2 of n, and so this is an example, and so this is we have a sequence A0, A1, A2, etc. such that the sum of an squared is less than infinity, n equals 0 to infinity. And the idea is that we would like to take it and extend the dot product that we have from, say, calculus 3 that you've seen over Rn, etc. And we'd like to be able to expand it here. And what's nice is that we have the Cauchy-Schwarz inequality, which basically tells us that if I take a sequence an and a sequence bn from our little L2 of n, then the sum an bn bar, I should also say that each of these guys are inside of the complex numbers, then this guy in absolute value is less than or equal to the sum of an squared times the sum of bn squared, and I need square roots here. All right, so this is by Cauchy-Schwarz. I think I've done this a number of times on my channel if you want to go look up some of that stuff. But essentially, the takeaway here is that the sum is well defined. And so what we do is we define the inner product as the inner product between an and bn is defined as the sum of an times bn bar, n equals 0 to infinity. And so this extends the idea of a dot product, which in turn takes with it an idea of angles, but this time between not two vectors in R3, but two entire sequences. So this is where Hilbert started. And he was looking at problems in differential equations and boundary value problems and stuff like that when he was working on this stuff. And then in the early 20th century, you had people like Maurice Furchet coming in and introducing and working on, in particular, I don't know if he introduced this space or not, but this is one of the spaces he was working on alongside Riesz, was this one. So the sort of Lebesgue space over an interval. Might as well just say, just say over an interval. So this is going to be a set of functions f mapping a, b to the complex numbers, such that the integral over a to b of the absolute value of f of x squared dx is less than infinity. And so Maurice Furchet, I think, actually was the first one to come up with the first version of the Riesz theorem, and Riesz was working on it. Even though they were collaborating on one paper, I guess he didn't know that Maurice Furchet was actually working on the same problem. And so I think he ended up scooping Furchet on this, if I remember right. And he ended up getting the credit for the Riesz representation theorem. Riesz also went on to get do a much more thorough version that didn't apply to only L2. But I thought that was really interesting. And so this is the Lebesgue space. Can't spell right now. I don't know why. Nerves, I guess. But yeah, the Lebesgue space. And so that gives us our first two versions of Hilbert spaces. And in this case, we have that if f and g are from L2 of, say, AB, then those should be, say, square brackets. Then we define the inner product between f and g as the integral from a to b of f of x times g of x bar dx. And again, the Cauchy-Schwarz inequality guarantees that this is well defined. And You can also take A and B. So this is on a closed interval written right here, but there's also a version of this that works over all of the real line, and that the theory there is a little bit different than what happens here. So it's a lot easier to work on L2 of an interval because you can show like continuous functions are dense in space by using things like the Weierstrass theorem and other things like that. But you can't use that same theorem for all of R because the Weierstrass theorem is made to work for compact intervals, and so you need to appeal to something else. And so I'll talk about that in actually one of my next videos that should be coming out soon, but we're not going to go too much deeper into that right now. The Hilbert space that I sort of got my start on was the Hardy space, and this is back when I was working on my PhD. And it's basically so H2 of D, Hardy space. So there's a couple of ways to look at this space. Personally, I think the easiest and most approachable way of doing this is just to look at this as the collection of generating functions for the little L2 space. So I'll write down. And so in particular, H2 of D, this is defined as the set, we'll just say f of z is equal to the sum of an times z to the n, where the sum of an squared is less than infinity. And we even go further than this, and we will say that the lost my train of thought. But essentially, this is taking sequences from little L2 and throwing them in there. And we should note a couple things. One, with this inequality here, this power series is convergent inside the disk. And so here I'm writing this blackboard bold D as all elements of the complex plane such that they are strictly less than 1. And so these are seen as functions over the unit disk. So this is one way of approaching this sort of thing. Another way is to start with the disk idea, and then and basically you take a look at sort of the norms on the scaled area, and then you take that up to the boundary. And if those stay finite, then you call those elements of the Hardy space. But I personally find this version a little bit easier. So then we can take this whole idea, and what we get then is that if F and G are elements of H2 of D, then we have what we call an inner product here, and this is actually the same inner product as you would have for the sequence space. So in this case, I'm saying that F is equal to the sum of A n z to the n equals 0 to infinity, and G is equal to the sum of Bn times Zn. Okay, so that's 3 different Hilbert spaces that we have defined here. I haven't told you what a Hilbert space is yet, but I'll tell you that in a second. But we have these things that we call inner products, and we have the space, the Lebesgue space over here. We have our sequence space, little L2, Lebesgue space over the closed intervals, etc. So that's all fairly nice. And then we have the Hardy space. What distinguishes these guys is, well, obviously, little L2 is just a sequence space. So that can be seen as a space of functions over the integers to the complex plane. So it's sort of a space for like discrete functions, if you like. The Lebesgue space is not technically composed of functions. It's composed of equivalence classes of functions that agree almost everywhere. So you can just change their value on a countable number of points or a finite number of points, and it doesn't make a difference. It'll still be the same function according to Lebesgue space. And so the Hardy space, what's significant about this is that this is a space of proper functions. So and so that distinguishes it from the L2 that we had before. So okay, so now let's talk about what is the definition then for a Hilbert space. So what do we have? So we say that a vector space, a Hilbert space, let's say, Hilbert space is a complete normed vector space where the norm is given by an inner product where an inner product is a function of two variables. So is a function of h cross h. Is a function that satisfies, is a mapping satisfying this guy. So one, we can have, so we're going to take f, g, and h inside of h, and we're going to let alpha, beta, and gamma be inside of complex planes, so complex scalars. And so what we end up getting then is we have that alpha f plus beta g inner product with h is equal to alpha times f inner product with h plus beta times g inner product with h. We have two that if you take f and g and you swap their order, it comes as a complex conjugate. Oops, not h, but f. It comes as a complex conjugate, which then tells us that we're going to be conjugate linear in the second variable. And then 3, f inner product with f is greater than or equal to 0, and equal to 0 only when f is equal to 0. Okay, so that's an inner product, and so we have several examples of inner products right now. So we have for little L2 of n, we have that the sum of an, bn bar. For L2 of an interval, AB. That's the worst B I've ever written in my life. There we go. No, oh my god. B. There we go. Then we have the integral of f of x times g of x bar dx. And then for the Hardy space, we also have the same inner product that L2 has, but in this case, the sequence is coming from the coefficients of the Taylor series. So that's what a Hilbert space is, and now we have several versions of a Hilbert space that we can look at. We have the Hardy space, we have the Lebesgue space, we have the sequence space, which is all very nice. So now, what is our next goal? Well, I want to tell you about two properties that are fairly nice. Sorry, getting over a cold. So let's see. And so these are going to become really important for talking about operators and bounded operators, etc. And so we have the Cauchy-Schwarz inequality. And so if H is a Hilbert space, with inner product, we'll say dot H, then we have that F, inner product of F and G is going to be less than or equal to the norm of F square root times the norm of G square root. And here the norm is given by the inner product, like I said. So it's F inner product G. Oh, yeah, there we go. And so yeah, not F inner product G. Oh man, that's what happens when you just do everything off the cuff. There we go. F inner product with F. So, okay, so that's rather nice. So we know that we sort of have an upper bound on any inner product according to the product of the norms of the functions that you're taking inner product with, which is pretty handy. That's going to be used a lot, actually, to get things like bounds on operators, etc. And then we have the Riesz representation theorem. So the Riesz theorem says that we're going to let H be a Hilbert space, and suppose that a mapping T from H to C is linear. And say continuous. What we also sometimes say in this case is that TF is going to be less than or equal to some constant C times the norm of F. It's boundedness. So boundedness and continuity are equivalent for here. Then TF, then I should say there exists an H, or exists a, I don't know, G inside of H such that TF is equal to F and a product with G. And so that's pretty nice. So that tells us that for a Hilbert space, the set of all functionals, that's what these are, the bounded linear maps from the Hilbert space to C. These can be identified with elements of H. So this doesn't always happen. So if you're working over Banach spaces, the collection of, or any normed vector space, the collection of of bounded linear functionals, or the dual space, it ends up being quite different from the original space. And so, but for the Hilbert space, the dual space is exactly the same as the Hilbert space. So you don't make anything new doing that. In Banach spaces, sometimes what you can do is you can actually take the dual. So in non-Banach space, but you can actually, in norm vector spaces, if you take the dual space and the dual space of the dual space, you can actually end up getting a completion of the original space, which is kind of cool. And so it's not a Cauchy completion, and it's not the completion in the sense of Dedekind cuts, but in the straight functional analysis way of doing things. But we can talk about that another time. In any case, so the Riesz representation theorem, it was initially put together by Maurice Furché for the Lebesgue space back in I want to say 19 teens. I want to say that's when people were first investigating the Lebesgue space, and Riesz put together, published his theorem, published his paper, and then in the 1930s, I think he published this more general for any Hilbert space version of this, and the Cauchy-Schwarz inequality itself goes back to 1800s with Cauchy, right? And so yeah. So these are some of the essential tools that we need from Hilbert spaces to really understand operators. Okay, so right now we have Hilbert spaces, and the Hardy space is one I'm going to talk about a lot, and we have these guys, a couple of theorems that we're going to leverage throughout this process. Okay, any questions? Anything I'm jumping over, not clarifying? I mean, it's please do speak up if there's anything you want to hear me say. Okay. All right. Well, let's see. Great. So, operators. Let's talk about them. All right. So, some operators. All right, so we're going to start with linear operators. So, I mean, the basic 101 version of an operator that most people probably have seen, if you're watching this far into this video, is matrices and things like that. We're going to talk a little bit more general and talk about a lot of other operators. In particular, we're going to have a favorite operator, which is going to be called the shift operator, and that's going to be over the Hardy space. And but let's go ahead and start off with a bounded linear operator. So, let's start with operators. So, given a Hilbert space, H, then we call T going from H to H a linear operator if T T of alpha F plus beta G is equal to alpha TF plus beta TG. And so if we satisfy that, we call it a linear operator. Now, in general, operators are really sort of any mapping between one Hilbert space to another or one Banach space to another. Just basically, usually think of it as like mappings of functions to functions. So filters are examples of operators. So if you have like a low pass or a high pass filter, then those are seen as being a sort of operator between signals, and usually that works over L2. And so in this case, this is just a linear operator, and that's what we have. We can also change this a little bit. So rather than just having from H to H, another thing we can do is we can define T to be operating on some subset of H. And so I can remove this and say it's going from some domain of H to H. And so here, D of H is just some set, or D of T, I should say, because it changes for T. So we can have some sort of domain. So T doesn't actually even have to be defined over the entire space H. For example, you can define a derivative operator. So D dt is, you could define it to be on some subset of the space of continuous functions. That's not strictly what we're talking about here, but because that's a Banach space. But yeah, you can talk about it like that. And so here we would define the set to be this would be C1, but it'd basically be F mapping 0, 1 to C, such that F prime is inside